eigenvalues and eigenfunctions in quantum mechanics. Welcome to LIB Academy, and in this video we are going to look at eigenvalues and eigenfunctions. Once again, this is also a video part of our playlist Quantum Mechanics or Quantum Chemistry. Before we start, let's look at some concept in mathematics. In matrices, sometimes multiplying a 2 by 2, let's say a 2 by 2 matrix by a vector, let's say 5, 2, vector x here and a matrix A here, we get a vector 9, 23, and we know that a vector is something that has a magnitude in its direction. This is one scenario, but in another scenario, like 6 minus 12 multiplying by the vector 5, 2, we get 3, 5, 2. So what do we see here? From number 1, we've seen that multiplying the matrix with this vector, we transform the vector into a new vector. So this vector 5, 2 is now transformed to 9, 23. But for this 2 by 2 vector, after we matrix, after we multiply it by our vector, we got the same vector here with a factor here. The vector, we got the same vector, but the vector is stretched by a factor 3. Here, vector pointing the same direction, but stretched by 3. Here, the vector is transformed. So this is what happens in some matrices. So in this case, let's focus on this. In matrix multiplication by a vector, sometimes you get a new vector, and sometimes you get the same vector that is either stretched or shrunk. So this brings in the idea of eigenvector. So in this case, this vector is an eigenvector. So this is just the mathematical meaning of the eigenvalue equations. Now let's go into details for now. Sorry. If we have an operator, let's say operator O, operating on a function f of x, and it gives us some constant or some term here with the same function. Here, this is our operator. We can see this is our eigenfunction. Eigenfunction. This is a combined word. Eigenfunction. And this here is our eigenvalue. Eigenvalue. Which is a constant and real numbers. Example 1, 2, 3, etc. And here is the same eigenfunction. So now we have an operator operating on a function, giving us a constant, emitting out the same function again. So in this case, we have an eigenvalue equation. The whole of this equation is called eigenvalue equation. Why do we need to know this? We'll talk about that before the end of this video. A simple example of this is, let's say we have operator A operating on the wave function phi to give us alpha and the same wave function phi. Notice that this eigenfunction is mostly a wave function. It's a wave function. This is a wave function or eigenfunction. And this is our eigenvalue, and this is the same eigenfunction. So we have an operator operating on a function to give us the same function at the end, at the other side with a constant, then a whole term becomes eigenvalue equation, right? And the function that the operator is working on is called an eigenfunction, right? An eigenfunction. That is what you should know now. Another example is the general, Schrodinger equation. This equal energy and then psi. You see, we have an operator operating on a function to give us the same function at the end with a constant. So this whole thing becomes eigenvalue equation. So why eigenfunctions and eigenvalues? Every single observable in quantum mechanics is going to have corresponding um, the corresponding eigenvalue equation of this format. Let's say we already knew that. Let's say if this operator operates on the function to give us E and the same function, so this becomes an eigenvalue equation. So every operator, every observable, and we said an observable is something that we can measure, right? For instance, momentum, position, energy, which can be kinetic energy or potential energy. So in quantum mechanics, the observable that we measure them are generally in this form, right? So there is a need for us to know eigenvalue equations, because in quantum mechanics we are not dealing directly with the observable, but we are going to have a wave function that can lead us to measuring the observable. Assuming we are to look at the observable, assuming we are to look at the position of an electron, and we've gotten some mathematical information about the position of the electron, which is the wave function psi, then looking for the appropriate quantum operator, if we operate it on the function, you see that we are going to get a value here. And this value, let's say, if it is a position, if this function is given the position, information about the position of the electron, this value is probably going to be the position of the electron. So let me write the general equation out. So we have an operator for an observable, for an sorry, observable operating on the function, operating on the function to give us value of observable of observable and the same function again, right? So this is what I want you to know. Every single observable in quantum mechanics is going to have this corresponding eigenvalue equation, right? If we operate operator for an observable, if it is position operator, we bring the position operator on the mathematical information about the operator, which is the wave function. We are going to get the value of the observable, the position, and then mathematical information again. So that is why we need to know eigenvalue equations, right? Well, we are just predicting, yeah, predicting the value. Well, we bring 2 out here, then sign is going to give us negative cos, right? Sorry, it should be positive cos. So cos 2x. Remember, we should have one of the derivative sign here. We are going to differentiate this again to get 2 by 2, giving us 4. Now derivative of cos will give us sign, which is negative. So negative sine 2x. All right. So now let's compare it to the previous one. To the other side of the equation. We see that here, this is a full equation. Sine 2x equal to this now minus 4 sine 2x. Yes, we have our function here and our function here, our operator here, and it gives us a value here. We still have our function at the right hand side, so this is an eigenvalue equation. And the function is an eigenfunction. So we have to show that the following functions are eigenfunctions under the operator d dx. So now let's start. The first one is e to the power I k x. So the operator is this, and this is the function. So d dx e to the power I k x is going to give us what? Bringing I k here, I k e to the power, I k e to the power I k x. So now let's compare. We have the same function on both sides, and then we also have a term ik right here. This ik here becomes our constant, right? Yeah. If it happens, okay. So this is an eigenvalue equation. So the other function is e to the power k x squared. So we have to differentiate. It's going to give us, bring 2 here, differentiate this time 2x k. So 2x k, then e to the power everything. So now is the function e to the power k x squared an eigenfunction? Now let's compare. We have the function here, but this constant, this is not a constant, right? Because we have the variable, the x being part of this whole term, so it makes this not going to be the same, constant, right? This will depend on the value of x. So this is no more a constant. So this is not an eigenvalue equation, right? So we pause here and continue in the next video. Thank you for watching. Feel free to support this channel by liking the video if you found it helpful. You can also recommend this channel to your friends. They might thank you.